Hi guys! In this lecture, we will learn more about stability and block diagrams. More specifically, we will study what stability is exactly and how it is achieved, and we will look more in details at block diagrams and how they allow us to conduct efficient calculations with transfer functions. First of all, let's talk about bounded input, bounded output stability, which is what you're mainly concerned about in control systems. So what it means is that any bounded input signal with a lower and an upper limit must produce a bounded output signal at all times with an upper and a lower limit as well, as you can see in this diagram. So here you have the input signal S in coming in, the transfer function GS with an output signal S out. So imagine you have any constant. Here we call it K in, which is a constant. It can be any number you want, okay? Not an infinite number, of course, but a number. Let's say 10 in this case, okay? So if S in is actually bounded by 10, so it's inferior to 10, okay, and the negative of S in is always superior to the negative of K in, so 10, okay? So this means that the absolute value of the input signal S in has to be inferior to K in or 10 in that case. It's exactly, then if that works, if this applies to the system, then it must be true as well for the output. So for the output, we will have a K out, which has to be a constant, but can be any other constant. It doesn't have to be the same. So for that constant K out, let's say 20 in that case, the output signal must be always inferior to K out, which is 20, and the negative of the output signal must also be always superior to minus 20, the negative of K out. So again, this means that the absolute value of the output signal must be inferior to K out. So in the end, bounded input, bounded output stability essentially means that the input signal, if it is bounded, so if it has an upper and a lower limit, then the output signal must absolutely also have an upper and a lower limit, although these limits don't have to be the same. So what are the conditions for bounded input, bounded output stability? Any linear system modeled by a transfer function is stable if and only if the poles of the system have negative real part. As we saw in the previous lecture, the poles are the roots of the denominator of the transfer function. It means that the poles are the values of S for which the denominator of the transfer function is equal to 0. As we discussed at the beginning of the lecture, and if you had a quick look at complex numbers before, you will know that a complex number is made of a real part, which is a normal number, and an imaginary part, which is a number multiplied by the constant j. And j is an imaginary number because it is the square root of minus 1, a number that cannot exist. Okay? So the complex plane is actually a plot of the real part on the horizontal axis and the imaginary part on the vertical axis. For a system to be stable, you want the roots, so that the real parts of the roots of the transfer function, of the roots of the denominator, sorry, to be negative, okay? So if you look at this plot here and you look at the two crosses, they're actually on the left side of the imaginary axis, which is the vertical axis. This means that the system is stable. If the roots were actually placed on the imaginary axis or to its right, then the system would not be stable. Okay, and that's very important. The imaginary axis is not part of the stable region. So to give you an example, if you have roots of minus 1 plus 3g and minus 1 minus 3g, then because the real part of that number, which is minus 1, is on the left of the axis, the imaginary axis, sorry, because it is negative, then the system is stable. However, if this minus 1 became a positive one, then the system would be unstable. Let's look at actual examples to better understand this concept. Okay, so we have here two differential equations. One is the second derivative of y plus the 2 times the first derivative of y plus 5y equals u. U and y being functions with respect to time. The other equation is exactly the same. However, instead of having plus 2 times the first derivative of y, you have minus 2 times the derivative of y. The initial conditions are 0 in both cases as well, and then we can write the transfer functions. So in the first case, you have that the transfer function is equal to 1 over s squared plus 2s plus 5, and in the other case, you have that the transfer function is equal to 1 over s squared minus 2s plus 5. So you can easily find the poles of these two equations. You will get on the left side that the two poles are minus 1 plus 2j and minus 1 minus 2j, while on the other side, where in the differential equation you had minus 2 times the derivative of y, the poles are actually 1 plus 2j and 1 minus 2j. So as we said earlier, in one case you've got a negative real part, and in another case you've got a positive real part. So what is the predicted behavior of this system? Well, the one with the negative real part is actually oscillatory but stable. It means that when you input a signal, it will first start to oscillate, but these oscillations will slowly and progressively die out. So this is a stable system where the oscillations die out. In an unstable system, these oscillations become worse and worse. So the system will start from not that oscillatory to maybe a bit oscillatory and will progress to extremely oscillatory. So the amplitudes of the waves, the oscillations become worse and worse and worse until infinity. This is an unstable system, and you can imagine now why they are so dreaded in control systems. It's exactly what you want to avoid. So now that we have gone through stability, and I hope that you understand, if you don't, please message me. I'm always very happy to help you and give you even more information about the subjects if you are interested. So yes, please message me if you have any questions. So now let's look into block diagram manipulation. We saw in the previous lecture that a basic transfer function can be expressed as an input signal, let's say us, going into the transfer function gs, which is the block here, and the output, and producing an output ys. Okay, so here you can write that ys equals gs times us. It's very simple. Let's now look at different configurations of block diagrams that can represent more complex systems, such as those that you would find in real life. So here we have a series transfer functions. You have a transfer function g2s taking in the output signal of another transfer function g1s. So first, let's look at g2s. So g2s actually takes in xs and outputs ys. So you can write for g2s that ys is equal to g2s times xs. Okay, now looking at g1s, it's exactly the same thing. You can see that g1s outputs xs for the input us. So you can write that xs equals g1s times us. But now, in the equation for ys, you can actually replace the term xs by g1s us. So you can see that ys is equal to g2s times g1s times us. So this is the full equation for these series transfer functions. It does make sense that xs disappears because g2s is essentially applied to the output of g1s, which is g1s times us. xs is just a construct that can represent the output of g1s, when the input is us, but if you put a transfer function after that, then this signal does not matter because it goes in straight in the second transfer function, right? So this is how you can write the equation for series transfer functions. Let's now look at parallel transfer functions. So what you have in this case is a signal US, which is going separately and independently into G1S and G2S. It is represented like this. You have the signal incoming, and then it splits at a junction to go in the two transfer functions. These transfer functions, because they are different, will output different output signals, right? So G1S will output Y1S, sorry, and G2S will output Y2S, okay? Then what you have is you have a sum, in this case, in this block diagram. It could not be a sum, it could be something else, but here you have a sum of the two output of these transfer functions to give the final output signal ys. Okay, so every time you have a block diagram, isolate each part, compute each part separately, and then put them all together. So start with the first transfer function, G1S. So you can write that Y1S equals G1S times US. You can then write that Y2S equals G2S times US. Okay, the final signal ys is going to be the sum of y1s and y2s. So you can then write that ys equals, in parentheses, g1s plus g2s multiplied by us. Let's have a look at an actual example of block diagram manipulation with two real transfer functions. So we have firstly g1s equals 1 over s plus 7. We then have G2S equals S plus 2 over S squared plus S plus 1. We're going to start with our series transfer function example. So like before, you can see that block diagram. You can then work out the equation for the output ys. You can do it again to check that you find the same result, and you get that ys is equal to G1S times G2S times US. So you can replace the transfer functions inside, so you get that ys is equal to s plus 2 over s squared plus s plus 1 multiplied by 1 over s plus 7 multiplied by us. And eventually, you can get the transfer function for that whole series transfer function system. Okay, you just divide the output by the input to give you the relationship between the two, and it's eventually going to be s plus 2 divided by, in parentheses, s plus squared plus s plus 1 multiplied by s plus 7. Now looking at the parallel transfer function example with exactly the same transfer functions, again you can rework out the equation for this configuration, and you will get that ys is equal to, in parentheses, g1s plus g2s times us, and then you can just plug in the transfer functions, develop everything, and you will get eventually that the transfer function for the whole system, ys over us, is equal to 2s squared plus 10s plus 64 divided by s cubed plus 8s squared plus 8s plus 7. As a little comment, you can also see here that the order of the numerator is lower than the order of the denominator, which is 3 here, while the numerator is 2, as it should be. This concludes the lecture on stability and block diagrams. I hope you enjoyed it. Please do not hesitate to contact me if you have any questions. Thank you, guys.